Commandos is a stealth game series developed originally in 1998 by Pyro Studios. One of its revolutionary effects was the cone of sight. The concept was simple. A cone is shown in front of the character, which represents his range of view. If the cone is occluded by an obstacle, that part of the cone won't be visible, giving the player a hint of whether or not he can be detected. This effect is applied similarly in other games like Desperados, Shadow Tactics, Invisible Ink, and even Brawl Stars. So how do we implement this effect in Unity? Before we start, I have created a basic scene with a couple assets from the asset store. Take a look at the description below to find out the assets that I have used for this project. Additionally, I have set the layers of all these objects to a new layer called Obstacle. To start with, we create a cube that is going to surround the character. This cube will represent his view area, although we will modify its size later from code depending on the view distance. Why do we use a cube and not a sphere? Well, a cube has fewer polygons and the end result will be the same, but what about a plane? Rendering a cube allows us to detect the intersection of the cube with the scenery and to render the effect even when the scene has level changes like steps or pits. Now that we have a scene, we are going to create a material and a shader that are going to work in a similar way that decals do. If you already have a decal system in your game, like the decals in the high-definition rendering pipeline, then you might want to integrate this effect within your system. In this tutorial, I'm going to assume that we don't have anything like that in our project. What we want to do in our shader is to detect the intersection of our cube with the depth buffer, so we only paint the fragments where the cube is overlapping the scenery. Please bear in mind that we want to apply this effect after the depth buffer has filled up with the solid geometry, so we have to change the shader hue to transparent. We don't want the shader to gride on the depth buffer, and in order to avoid Z fighting, we deactivate Z griding. We include the depth buffer to our shader using the camera depth texture. Unity will fill this texture for us. That comes for free when using deferred rendering or when using shadows in forward rendering, so make sure you are using the right settings or make the camera to use the right depth mode. In the vertex shader, we transform vertex to clip space as usual, but we also get the vertex on view space. We need to negate this vertex Z coordinate because the camera view matrix follows OpenGL conventions where the camera points towards negative Z. We do this in order to have the ray from the camera to the vertex, which we will need to check the intersection with the depth buffer. Additionally, we get the screen UVs using the Unity function compute screen pause that we will use to sample the depth buffer. Now, in the fragment shader, the first thing to do is to stretch that ray to the maximum size, which is the size of the camera frustum. We achieve that scaling the ray by the far plane divided by the Z position. We want to sample the depth texture using the screen UVs in order to get the depth from our camera. We use the built-in macro called SampleDepthTextureProj, which will project the coordinates for us and get the depth from the red channel of the texture. Then, we linearize the depth and scale the ray by the linearized depth, which gives us the position of the ray intersection with the depth buffer in view space. Finally, we convert that position to wall space, which is the point in this image, ray scale by linearized depth converted to wall space. At this point, we can check if the fragment lies on a horizontal surface, so we don't render the cone on walls and other vertical objects. In order to do that, we use a shaded derivative to check the adjacent world position. I don't want to get into much detail here about what shaded derivatives are and what they are useful for. I will leave a link in the description with more information. For now, you just want to know that a shaded derivative allows us to get the difference of a value that we pass as a parameter with an adjacent pixel. And this is possible because GPUs evaluate pixels in blocks of 2 by 2, so we can calculate the dot product of the derivative of the wall position with the up vector and discard the fragment if it is considered vertical enough. The closer this dot product gets to 1, the more vertical the surface is. Finally, we transform our position of the depth buffer to object position and check if the hit lies within the cube coordinates. If it does, then that means our cube is intersecting the depth buffer. If it doesn't, we can safely discard this fragment. With this, we finally have the right intersection of the cube with the scenery. Now, I modify the alpha of the final color using the distance from the center to get a circle. In addition, I add an inner circle so the effect is not drawn at the character's position. We also need to check the angle of the local X and Z coordinates to see if the fragment lies within the specified view angle. The next step is to check if the fragment is occluded by an obstacle. To do this, we are going to use a similar technique that is used for shadow mapping. First, we need to create a camera that renders the scene from the character's perspective. This camera will only render the objects in the obstacle layer. Before we move on, we create a component called Cone-of-Sight Renderer, which will modify the camera so it only draws to a depth texture. We set the far plane to match the view distance and the field of view to match the view angle. As an additional step, we modify the cube scale to match the view distance so the camera and the cube have the same size. We also make a copy of the material and bind the depth texture of our camera to the material. On the component update, we render the camera view and pass the camera view projection matrix to the material, which we will need later in the shader to check the occlusion of fragments. Now, back in the shader, we want to check the occlusion of the wall position. As I said, this is very similar to shadow mapping. First, we transform the wall position to the camera space and convert those coordinates to normalized device coordinates, which means make them go from -1 to 1. Then we transform these coordinates to a range of 0 to 1 so they can be used as UV coordinates. Finally, we sample the depth texture. We subtract the C coordinate from the sample depth from our C in view space. If we get a positive value, it means something is occluded in the view position we are sampling. A negative value would mean that the view position is actually closer and therefore not occluded. In case you're wondering, we have used a bias value to prevent artifacts. We use this occlusion value to pick between two colors that will give the player a hint of whether or not he could be seen. You can simply clip the fragment if you don't want to show anything when it is occluded. Finally, we add some stripes just to make the cone look a bit better. It doesn't look that great, so you might want to spend a bit more time than I did on this. Adding some patrolling behavior to our soldiers and stealing music and sound effects from the Commandos remaster, this is how it looks like. All the code will be available on GitHub, so if you're interested, find the link in the description below. Remember to like, subscribe and leave a comment with which game effect you would like to see next. Thank you for watching and see you in the next video.